Okay, my name is Zezhou Li. My PhD advisor is Professor Mark Myers. It's a great honor to have opportunity to present my PhD thesis work and the dynamic PhD thesis presentation. My PhD thesis is the dynamic behavior of two advanced materials, the ultrafine-grained titanium and high-entropy alloys. The structure metals has lots of different applications. Until recently that the nanocrystalline metals and high-entropy alloys was developed. The nanocrystalline metals has a grain size less than 100 nanometer, which has a higher strength in comparison with coarse-grained materials due to the significant reduction of the grain sizes. The high-entropy alloy was developed since 2004 with the mix of 5 or more elements equally or near equally, which obtains high failure stress and high fracture toughness. However, their dynamic response and the failure mechanism were not well studied, so it's of great significance to study their high stress rate behavior for further aerospace or industry applications. My PhD thesis is mainly focusing high stress rate behavior of two kinds of advanced materials. One is ultrafine-grained titanium with high strength. Another is cobalt, chromium, nickel-based high-entropy alloy with high strength and remarkable fracture toughness. The ultrafine-grained titanium was made by severe plastic deformation method, which is called eco-ago channel compression. By subjecting the coarse-grained materials to different deformation levels, one can achieve different grain sizes, such as 500 nanometer and 100 nanometer titanium. We examine three different kinds of the high-entropy alloys. The one on the most right shows some pores which was induced by the powder metallurgy method. We also subjected the cobalt, chromium, iron, manganese, nickel high-entropy alloy to severe plastic deformation method. Lots of slip bands can be observed by the ABSD image, and by this, the stress of the material can change significantly. We mainly focus on the high stress rate behavior of those two kinds of advanced materials, especially adiabatic shear localization phenomenon. As discussed just before that, we also mainly use the Split-Hopkinson pressure bar for our dynamic testing. The middle figure shows the Split-Hopkinson bar in our lab. The samples are right-damaged in the instant bar and the transmitted bar. When the projectile hits the instant bar, it will produce a straight wave and propagate into the specimen. It will then split into the transmission wave and the reflected wave. By attaching the strain gauge of the two bars, one can get the deformed information of the specimens. We mainly use two kinds of the geometry of the specimen. The cylinder samples were used to test the mechanical behavior of the material at different strain rate and temperatures. This hair-shaped specimen were used to induce the forced shear band inside the samples. The adiabatic shear localization is an important failure phenomenon for metallic materials under high stress rate loading. It occurs when the thermal softening suppresses the straight hardening and straight rate hardening. The stress will drop suddenly, and due to the significant temperature rise in a very narrow region, the microstructure will also change significantly. We will present the microstructure inside the shear band in the following presentation. We first examine the dynamic response of ultrafine-grained titanium. The TEM observation shows the average grain size of the titanium with 500 nanometer and 100 nanometer. The diffraction pattern confirms the single-phase hexagonal closed package microstructure. The mechanical response of the material at various temperatures shows that by decreasing the grain size into 100 nanometer, the strength of material can increase from the 500 megapascal to over 1.5 gigapascal. So further decreasing the testing temperature to liquid nitrogen, temperature 77 K, the strength can increase to over 2 gigapascal without rapid loss of. So how about the adiabatic shear localization phenomenon? We use this hash specimen try to induce shear band in titanium with different grain sizes. We found all the shear band in the tested materials. The SEM image in the bottom shows the formation of the shear band inside the ultrafine gradient 100 nanometer titanium. The width of the shear band around 2 micrometer. We use the focus RB technique to get the TEM sample right in the middle of the shear band. For mechanical responses, we found that with the decreasing of the temperature, the shear stress can reaches over 1 gigapascal without lose the stress rapidly, even at 17.7 K. What is the microstructure inside the shear band? We put our TM sample under the advanced machine and found that there are a mixture of the elongated nanobottles and equal X or near equal X the nanograins inside shear band. Outside the shear band, as shown in the B, there is significant growth, which was merely formed during the cooling process of the shear band. Based on what we observed by the TEM, we propose a rotational dynamic recrystallization mechanism inside shear band for ultrafine gradient titanium. Under applied shear strength, the ultrafine grain will first form the elongated configuration. With further increase of the shear strain, the dislocation density will increase and it will pile up to form the low-angle grain boundaries. When the temperature rises significantly inside the shear band, the grain will start to rotate through the grain boundary diffusion processing, as shown in the bottom three figures. Finally, the equal X grains with the grain size less than 100 nanometer will form. Thus, the ultrafine gradient titanium indeed increases stress under dynamic loading without rapid loss of stress. But are there any structural metallic material can perform the better resistance to shear localization? At the same time, we also examine the advanced cobalt chromium nickel high-entropy alloys. This kind of high-entropy alloy has a low stacking for the energy and a high strain hardening rate, high strength, and high fracture toughness. It can even increase its fracture toughness at lower temperature due to higher strain hardening rate. We first examine the mechanical response of the aluminum, cobalt, chromium, iron, nickel high-entropy alloys. We found that at both low strain rate and high strain rate, the high strain hardening rate was kept in comparison with the pure aluminum. It can increase the stress from the 400 megapascal to over 800 megapascal at the strain of the 0.25. This material has very high strain hardening rate and strain rate sensitivity in comparison with the pure aluminum. This high strain hardening rate suppresses the thermal softening effect of this alloy under dynamic loading. So why does this material has such high strain hardening rate? We examine the microstructure at different strain rate. At low strain rate, we observe loss of the forest dislocations. Thus, the high strain hardening rate is mainly arises from the solid solution hardening. At high strain rate, we found loss of deformation twinning. This twin boundary can stop the dislocation motion and raise the stress of materials continuously. The low stacking for energy in cobalt, chromium, nickel-based high-entropy alloy leads to the formation of mechanical twins more easily, leading to high strain hardening rate behavior. We then try to induce forced shear localization inside this alloy. However, no shear band was found at a shear strain about 1.1. The ultrafine gradient material was localized at a shear strain around 1. Why does this happen? We examined the microstructure near the inserted tip and found lots of mechanical twins that even interact with each other and cut through with each other and leads to the formation of the small blocks to restore the dislocation, leading to the high strain hardening rate. This high strain hardening rate suppresses the thermal softening, leading to the retarded formation of the shear localization. We then give the reasons for the remarkable resistance to shear localization to this alloy. We use the wrench and shear instability criteria for the offset formation of the shear bands. It's supposed to occur when the thermal softening suppresses the strain hardening and strain rate hardening, and then the shear stress drops suddenly. We implement the Johnson-Cook model inside this shear instability criteria, and at a strain rate about 10,000 per second and shear strain 1.1, the high strain hardening rate suppresses the general thermal softening value significantly, and D shear strength by D shear strain is much larger than 0. A much large deformed shear strain and temperature raise required to activate the shear strength, shear localization formation in this alloy. However, due to the limitation of our materials, we didn't find the critical shear strain for the formation of shear band inside these materials. We then get more materials for another cobalt, chromium, iron, magnesium, nickel high-entropy alloy. This is also called the Cantor alloy because it's developed by Professor Brian Cantor from the Oxford University in 2004. And this material has very high fracture toughness. We then control the displacement by the stopper ring for the head-shaped specimens. We test the material under dynamic loading and found only the one with the highest displacement, 2 mm, formed the shear band. This is corresponding to a very large stray 7. So why does this material has such remarkable resistance to shear localization? We examined the microstructure before and after shear localization. Quite similarly, we found lots of deformation twinning was formed under TEM opposition that cut through the initial coarse grains, and lots of dislocation was stored inside the material to provide high shear hardening rate. At a very large shear strain about 7, the temperature raised inside the narrow region and the dynamic recrystallization occurs. This leads to the formation of the ultrafine grains inside shear band. Differently from the shear band in ultrafine-grained titanium, lots of neo-nanotone was founded to reduce the dislocation density and overall strain energy inside the shear band. We propose the shear localization mechanism in the anneal cobalt, chromium, iron, magnesium high-entropy alloys. Due to the low stacking for the energy, the mechanical twinning are easily formed under dynamic loading. It will then cut through the coarse grains and for the different blocks for dislocation motion to give rise to the high shear hardening rate. Until very large stray about 7 accumulated heat will rise more significantly and trigger the dynamic recrystallization inside the shear region. The nanotwin was formed inside the ultrafine small grains to reduce the overall strain inside the. Our study indicates that the low stacking for energy high-entropy alloy can have very high strain hardening rate, which give indication for the development of the advanced metallic materials with resistance to shear localization. However, the yield stress of the annealing cobalt, chromium, iron, magnesium is pretty low. Thus, we submitted this anneal sample to the severe plastic deformation. The microstructure shows that the swagged cobalt, chromium, iron, magnesium high-entropy alloy has lots of the defects, such as dislocations, grain boundaries, slip band, and even stacking fault was formed. All these defects give rise to the stress of the materials, and now the yield stress can reach near 1 gigapascal. An amazing finding is that under quintet compression till true strain about 0.2, this material didn't fracture. And at a higher strain rate, it can even reach 4 gigapascal with a failure strain about 1.5. Why does this material deform so severely? Can still deforms and providing high strain hardening rate and high strength. We examined the microstructure after deformation and found that in addition to the dislocation motion and mechanical twinning, there's the FCC to HCP phase transformation and amorphization band was revealed. Due to its low stacking for the energy, the partial dislocation can slip very easily to this with further increase of the strength and strain rate. The amorphization will nucleate at the intersection of the either stacking faults, twinning, and new phases. The strength concentration in the small area is really high, and dislocation density is also really high. This will rearrange the ordered atom into disordered configuration and form the amorphization nuclei sites. It will then propagate along the shear direction to form the amorphous band. We propose that this FCC to HCP phase transformation and amorphization can give rise to the stress of the high-entropy alloy and provide significant plasticity also. As a summary, we compare the critical shear strain for shear localization of ultrafine gradient titanium and high-entropy alloys. The high strain hardening rate, where Na is the strain hardening exponent, can indeed suppress the thermal softening inside the cobalt chromium nickel-based high-entropy alloys, our study gives the indication for the development of the advanced metallic materials very resistant to the shear localization. Another summary figure shows the observed dynamic loading strain energy of different structural materials. Our results show that the pre-deformed contour alloy achieves the dynamic loading strain energy in comparison with alloy, steels, coppers, and ultrafine titanium due to the phase transformation and amorphization. Also, the combination of excellent strain hardenability and general thermal softening effect of the cobalt chromium nickel-based high-entropy alloy give rise to remarkable resistance to shear localization. In addition to that, the ultrafine gradient titanium has a higher stress compared with coarse gradient titanium under dynamic loading. Last but not least, our PhD research provides scientific methods such as decreasing grid size, decreasing stacking forward energy, and increasing dislocation density to develop impact-resistant advanced materials. I would like to acknowledge the support of dynamic organization and committee member to provide this precious opportunity to present our PhD thesis work, and my PhD committee members, all collaborators, and funding resources were also greatly appreciated for the support of my PhD research. Thanks so much for your attention.